Okay, so welcome everyone to this new session of the One-Word Probability Seminar. It's a pleasure for us to have the two speakers of today, which are Eleanor Archer and Anita Winter. The first speaker will be Eleanor Archer from Paris-Dauphine University, and she will talk about scaling limits of high-dimensional uniform spanning trees. And please, Ellie, you can start.
Great. Thank you to Roger and Louisa for the invitation, and thank you everyone for coming. So today I will talk about, as Louisa said, scaling limits of high-dimensional uniform spanning trees. And this is all based on joint work with Asaf Nachmias and Matan Shalev from Tel Aviv University. So I will start with the definition of spanning trees if you haven't seen it before. It's just what you think. So if you have a graph G, so by this I mean I just have a series of vertices connected by edges, then a spanning tree of G is just a connected subgraph which contains every single vertex, is connected and has no cycles, just like in the picture. And I'm interested in studying random spanning trees, and possibly the most natural model of spanning trees is what we call the uniform spanning tree. And this just means that if we take a finite graph G, of course, the number of spanning trees of G will be finite, so we can just pick one uniformly between all of the spanning trees, and this is the uniform spanning tree of G. And it will be denoted by USTG throughout the talk. So I'm interested in, well, there are many questions you can ask about spanning trees, uniform spanning trees, but I'm interested more in the macroscopic properties, so what they look like at large scales. And the first thing you can wonder is whether the macroscopic geometry of spanning trees, uniform spanning trees, will depend on the graph or not. And of course, you expect that certain properties of uniform spanning trees will depend on the graph, but actually the uniform spanning tree is an example of a nice model from statistical physics, whereby for a large class of graphs, which we call in some sense high-dimensional graphs, actually the macroscopic properties of the uniform spanning trees are always the same and actually don't depend on the precise choice of graph. And this is a phenomenon known as universality, and it's what I want to talk about today in terms of the scaling limit. And when I say scaling limit, what I'm particularly interested in is the metric space scaling limit of this uniform spanning tree. So for example, in the picture, if I take two vertices of this graph G, the distance between them, according to the spanning tree metric, is just the length of the path in the spanning tree between the two vertices. And so the spanning tree, the uniform spanning tree is a metric space, a random metric space. And what we can also do is endow it with a random measure, which is just a uniform measure on its vertices. And before launching into the story of the scaling limits of uniform spanning trees, I will just mention that actually this is a very popular model in statistical physics, and it has lots of nice connections to combinatorics and physics and electrical networks. And it's a very nice model, and there are many books about this. So if you're interested, I encourage you to read. But okay, back to scaling limits. So I said maybe, I already gave you a spoiler that actually the scaling limit is the same on a large class of high-dimensional graphs. And so the best way to get intuition on what happens on high-dimensional graphs is to look at the complete graph. And in the case of the complete graph, because everything is symmetric and all the edges are there, actually, the uniform spanning tree of the complete graph is just a uniformly chosen tree with labeled vertices, vertices labeled from 1 to n. And this means actually we know how to study it using other techniques. And it was a result of David Aldous and later Legal in this topology, that if we take a uniform labeled tree on n vertices, so this is the uniform spanning tree of the complete graph with n vertices, and we endow it with this metric I talked about, so just the graph metric on the tree, intrinsically on the tree, and we rescale this distance by square root n. And we also take the uniform measure on the vertices, so here I'm letting mu n be the counting measure, and I'm dividing by n to get the uniform measure. Then this converges in a topology, which I will explain shortly, to something which we call the Brownian continuum random tree. And so to get an idea of what this continuum random tree is, I've shown you two simulations below. Unfortunately, neither of them are by me. But it's essentially a very nice random fractal tree, and it's really the equivalent of Brownian motion, but in the world of random trees, in the sense that it's also a universal scaling limit of many random tree models. And so what we wanted to do with Asaf and Matan was try to extend this result to other high-dimensional graphs, which maybe are not quite so high-dimensional as the complete graph.
Mu n is probability measure, or?
So mu n is the counting measure, So when I renormalize by n,
constant. Mm-hmm.
Uniform.
Okay, thank you.
Okay. And by the way, really don't hesitate to interrupt me if you have questions, because it's always good to have questions. Okay, so I will tell you what our result was with the Saf and Matan a couple of years ago. So we studied instead the UST of the torus, and we showed that if you restrict the dimension strictly greater than 4, then essentially the same result is true. You can take the uniform spanning tree of the torus with n vertices. So I've parameterized it like this so that there are always approximately n vertices in total. You rescale the distance by square root n, and there's also a constant. You take the uniform measure on the vertices, and this converges again to the Brownian CRT with respect to this topology, which I haven't yet defined. And so this is a universality result. And over the course of the talk, I'm going to explain some of the things. So I'm going to explain in a moment what this GHP topology is. I'm going to explain why we have this condition of dimension strictly more than 4. And then I'm going to give you a construction of the Brownian CRT and try to explain some of the heuristics behind the theorem. Okay, so this is the first thing. It's called the Gromov-Hausdorff-Prokhorov topology. And this is a topology for metric spaces equipped with a measure. And if two spaces are close in this topology, this means that we can embed them isometrically in a common metric space, such that the Hausdorff distance between the two sets is small. That's the H. And also so that the Prokhorov distance between the two measures is small. So that means roughly, if I take a small ball in the blue tree, then I can also take a small ball in the red tree, which is very close to it and which has roughly the same measure. And so this is actually quite a powerful topology, because once you have GHP convergence of metric measure spaces, you also get several other things for free. And the first thing you get for free is that the diameters of the spaces also converge. So in the case of the complete graph, you get that if you rescale by square root n, it converges to the diameter of the Brownian tree, the CRT. And of course, in the case of the torus, you just have to add the beta here and you get the same thing. For trees, you also get something called the height converges. So I didn't really mention it, but you can also define a root. So in the torus, you can take your root to be the origin, the vertex, which was the origin. And in the CRT, you can take a uniform point to be the origin or the root. And you can actually root your trees. And actually, you get that the height of these trees also converge when you rescale by the same thing. And it just turns out, so I won't explain this today, but actually the height of the CRT has a nice law in terms of a Brownian excursion, which comes from the construction of this CRT from the Brownian excursion. And finally, so this is a result which is...
Sorry, very stupid question. What does height mean?
Sorry, so the height is the maximal distance between, I can actually write it. You take a vertex in the tree and you take the maximal distance between a vertex and the root of the tree. So you have to root them.
Okay, thank you. Sorry.
That's okay. That's a good question. And so you get convergence of this as well, at least in this case. And then finally, you also get convergence of simple random walks on the spaces. And this is really only true on trees in general, that this GHP convergence gives you convergence of the simple random walk. And that's because on trees, this shortest path distance we considered is also equivalent to what we call the resistance metric, which tells you something about random walks. And once you know about these, there's a general result of David Croydon, which tells you that a consequence of our GHP convergence is that the simple random walk on these trees also converge to some notion of Brownian motion on the CRT, which can be defined rigorously, but which I won't define today. So that's some motivation for why we want to consider this GHP topology. And then I also said I would explain why we have D at least 4 in our condition. And to understand why we have D at least 4, I have to explain to you how you sample uniform spanning trees. And maybe lots of people have seen this before, but it turns out that there are lots of links between uniform spanning trees and loop-erased random walks. And so by loop-erased random walk, I mean roughly that I take a random walk trajectory and I just erase the loops. But I have to be a bit more precise. I have to really spell out too that I'm going to erase loops chronologically. Because otherwise, if my random walk does something like this, depending in which order I erase the loops. So for example, if I, let's see, I could actually have a loop starting here and the random walk goes all the way around there. So if I erase this red loop, then my loop array's trajectory is just this part of the trajectory here. Whereas if instead of doing erasing loops in that order, if I had instead said, okay, I will first erase this loop, and then I will secondly erase this loop, then I actually get a different final trajectory for my loop arrays random walk. So we have to specify in which order we erase loops, and we specify that we erase them chronologically, which actually corresponds to the second image. And that just means that I run my random walk, and at each time I create a loop, I immediately erase it and I continue. So it's some chronological notion. And it turns out that these loop erase random walks are the building blocks for building uniform spanning trees. And there's a nice algorithm of Wilson which tells us why. So I will tell you the algorithm. It goes as follows. It's a bit magic the first time you hear about it. And so what you should do, so by the way, this algorithm, it works on any finite graph. If you have any finite graph, this algorithm will sample a uniform spanning tree of that graph. And so you start by labeling the vertices of the graph in any order you like. There's no restriction on the order. And the aim is to build the uniform spanning tree branch by branch. And you first sample the branch between V1 and V0. Then you add in the branch from V2 to what you already made, etc. And so our first tree, which has 0 branches, is just vertex V0. For our second tree, we take the vertex V0 and we take our vertex V1 and we just sample a loop erase random walk from V1 until V0. So we sample our random walk and then we erase the loops, and we have a path from V1 to V0. Then we continue. So after our first step, we have something like this, and then we add V2, and so maybe V2 is over here, and we sample a loop erased random walk which starts at V2 and it just stops the first time the random walk hits what we already constructed, and we keep going. And this amazing result of, okay, so for example, if V4 is already in there, we just don't do anything at that step. And this really lovely result of David Wilson says that the tree we get at the end has the same law as the uniform spanning tree of the graph, which is very nice and very useful because this gives us really a concrete way to sample uniform spanning trees, which my original definition as just a tree chosen uniformly in some set did not. And we can use this algorithm to understand why we have this condition D at least 4, at least heuristically, because the algorithm tells us that the structure of the uniform spanning tree depends on a couple of things. So it depends on the structure of these loop erased random walk trajectories. And it also clearly depends on intersection properties of random walks and loop erased random walks, because you end your process for forming one branch when a random walk hits a loop erased random walk. And if you just look at this second condition for a moment, you can make the observation that on ZD, so not on the torus, just on ZD for the moment, if I take 2 independent random walks started at the origin, and I want to look at how many intersections they have, then actually this expected number is finite if and only if D is greater than 4. And there's the same kind of heuristic on the torus. And this heuristically says that if D is greater than 4, then a random walk trajectory won't intersect itself very much, and that macroscopically loop erased random walks look like random walks. And for example, the scaling limit of a loop erased random walk in dimension strictly greater than 4 will still be Brownian motion, just like for the random walk. And we see the same kind of phenomena occurring on the torus, and so this is why on the torus we also have this what we call mean field behavior, so this universal behavior strictly above dimension 4. Okay, so I explained a couple of things from the theorem. Now I want to explain to you what this Brownian CRT is. And so there are a few constructions of the Brownian CRT. You may have seen one using a Brownian excursion. I'm going to give you a different construction today. This is due to David Aldous in the 1990s, and it's called the stick breaking construction. And it goes as follows. So you start by taking the positive real line, and you just throw some Poisson points on this real line with intensity x dx. So as you go closer and closer towards infinity, you have more and more points closer and closer together. And just to be consistent, you also add a point at 0. And the idea is that each interval between 2 points is going to be one branch of the CRT. And the idea is to use these points to divide the positive real line into sticks or into branches, and to glue these branches together inductively to construct a random tree. And it turns out that this is actually a very nice construction and has a very nice limit, which is the CRT. So I have a very basic set of images showing this. So first you take the first stick, which just has some length, and you just take a stick of this length. This is in some sense your T1. You then take the second stick, so you take a stick with distance equal to, with length equal to the distance between these two Poisson points, and you attach it to a uniform point on the first stick. So to define a uniform point, you can just renormalize Lebesgue measure on the first stick. And then you continue. So you take your third stick and you take a uniform point of the union of the first two sticks, so on what you already constructed, and you attach this third stick. And you keep going and doing the same thing and attaching lots of different sticks. And you can ask yourself, if I keep going forever, what happens? Will I find something compact, finite? Will it be infinite? And actually, what David also showed is that if you keep going forever, you can construct a nice fractal tree. And this fractal tree is exactly what we call the continuum random tree. And of course, to do this formally, you have to embed things in the right space. So if you want to do it formally, you should really embed this whole process in L1. And the way you do that is each stick corresponds to a new direction in L1, and you can really use this to asymmetrically embed the trees you're constructed in L1 in a way that they will be trees. And this enables you to take limits with respect to the L1 distance, etc. And you should also take the closure, it turns out. But this is the construction to have in mind. And it also allows you to define a measure on the limiting tree, because at each step of this algorithm, you can define uniform measure on the tree you've constructed up until that point, just by renormalizing Lebesgue measure. And you can also take the limit of this measure in this space. And this limiting tree, once you take the closure, it's a compact metric space, and it's exactly the Brownian CRT that we saw on the first few slides. Okay, so that's the construction we're going to work with today. I want to explain a bit now about the convergence in the theorem. And one thing I should mention first is that actually, this is not obvious, but in this construction, the ends of the sticks also correspond to uniform points in the CRT. So if you want to know the distance between two uniform points in the CRT, it's actually just equal to the length of this first branch, etc. So this is quite useful for us, actually, because the heuristic behind the convergence of the theorem we saw is that if you take this first algorithm we saw, Wilson's algorithm, and you run the first case steps, so you fix k, say you take k equals 10, and you run the first case steps of Wilson's algorithm on the torus. The idea is that at large scales, this is kind of doing the same thing as the first case steps, the first 10 steps of the stick breaking. And it means that in the end, the two algorithms, Wilson's algorithm is really approximating the stick breaking algorithm. And this claim here is some sort of finite dimensional convergence of the uniform spanning tree of the torus to the CRT. And I will actually explain to you a bit more precisely why this is true. But to keep things simple, I will just explain to you why it's true in the case k equals 2, so when you have two uniform points, and for the complete graph. And then I'll explain to you afterwards how you can modify it to prove the same result on the torus. And so what you have to prove for the k equals 2 case, you just have to prove that the length of the first branch you construct in Wilson's algorithm converges to the length of the first stick in the stick breaking process. And in terms of the stick breaking, it's very easy to calculate the law of the length of the first stick, because what does it mean for this distance to be bigger than y? It means that in the interval from 0 to y, you do not throw any Poisson points. It means your first Poisson point was strictly to the right of y. And so the probability that this happens is just the probability that a Poisson random variable, where we integrate the density over this interval, is equal to 0. And so my density was xdx. So you can just calculate directly that the probability that this distance in the CRT is bigger than y is given by exponential minus y squared over 2. I didn't write it, but this is called the Rayleigh distribution. I think it will also be useful in Anita's talk. So once you have that, what we would want to prove is that the same thing is true on the UST in the limit. So how do we do that? We have to analyze the first step of Wilson's algorithm when we start with uniform points. So I did tell you actually that in Wilson's algorithm, you can start with any ordering of the vertices. So it means you can actually just take a uniform ordering so that the first 2 points in your sequence will essentially be uniform, or will be uniform. They're just conditioned to be different in the graph. And there's a nice result. So a priori, it's quite hard. It seems like it's quite hard to calculate what's the length of this first loop erased path you sample in Wilson's algorithm, because it's a loop erased random walk. And although random walks are nice Markov processes, the loop erasures are not. And so it seems quite difficult to do it. But actually, if you think a bit, you can kind of realize there is a formula which allows you to relate loop erased random walk transition probabilities to random walk transition probabilities. And it goes as, it goes as follows. So let me draw. So in the first step of Wilson's algorithm, I'm going to take 2 uniform points, say UN1 and UN2. And in the first step, I sample a random walk from UN2 to UN1. And in the end, I want to calculate what's the probability that the length of this loop erased random walk is bigger than y, or y square root n, say. And so it means I want to, for example, condition on, well, first I can write the probability that this length is bigger than y times square root n. It's just a product from I equals 0 to y square root n, maybe minus 1. The probability that the length is bigger than I plus 1, given that it's bigger than I. I can just multiply these probabilities and I get this probability. And if I want to calculate one of these probabilities in the product, it means I have to condition some loop erased random walk trajectory to really survive for I steps away without hitting this UN1. And I want to know what's the probability that it will go somewhere else at the next step compared to the probability that it goes directly to UN1 on the next step. And because this loop erased random walk is not a Markov process, it's not obvious at first, but you have to think about what does it mean if I want to really condition on this trajectory being my loop erased, the first I steps of my loop erased random walk trajectory, what does it really mean? And you really have to think about the last time the random walk is at this point. And what's true at the last time is that I run some random walk, and then at the last time, the loop erasure up until that time is precisely equal to this trajectory. And then afterwards, my random walk cannot come back and hit my past trajectory, because otherwise it will erase parts of the part which I need to be there. It's not possible. But since I know that I will actually kill my random walk at the instant it hits this point UN1, it means that afterwards, I'm just conditioning my random walk to hit this point UN1 before I come back and hit my past trajectory. And so this is what the Laplacian random walk representation says. It says that if I have a random walk x between 2 vertices, so from UN2 to UN1, and I let ym be its loop erasure, then if I want to condition on the first I steps of the loop erasure, and I want to know what's the law of the next step of the loop erasure, it's like the same transition probability for a random walk to make this step, but it's a random walk that's conditioned. So tau here is my hitting time for a random walk. It's conditioned to hit this UN1, this termination point, before it returns to this past trajectory. And this formula is really the key to proving this result, at least on the complete graph. Well, actually, there are many ways you could prove this result, but it's the key to the way I want to explain to you. Because, let me see. We can rewrite it like this. Here I've just separated the first probability. So I had a conditional probability, so I can just write it like this. It's the probability that a random walk makes a jump, but it's weighted by these hitting probabilities. Firstly starting at V, and then in the denominator starting from Yi. And on the complete graph, so I will just explain it on the complete graph. We know how to estimate these probabilities because everything is symmetric and everything is very nice. So what happens on the complete graph is that we want to calculate this probability, like I said. And what's actually easier is to calculate 1 minus this probability. So let me just undo it again. It will be easier to calculate 1 minus this, because 1 minus this is just the probability that my next step is the final step of the loop erased random walk. So it's just the probability that I jump to this n1 on the next step. And then lots of these terms become a lot easier to analyze. For example, so now it's the same thing, and my thing's not aligned. This probability in blue here, if my v is un1, it's just going to be 1 over n minus 1, because it's the complete graph and all of my jumps have equal probability. This red term, if my v is un1, is just equal to 1, because of course, if I start at un1, then I really do hit un1 before I hit this past trajectory. And finally, this term in the denominator, this is going to be roughly, well, the probability that I hit un1 before I hit this past trajectory is roughly proportional to the ratios of the sizes of these sets. So this set has size 1, this set has size I roughly, so it's going to be roughly 1 over I. And so when you put, by the way, this should maybe be a 1 here in this exponent. So once you put this all into the formula, you get that the probability that your loop erased random walk, which started at your second vertex and is going to your first vertex, so given that it survives for time I, the probability that on the next step it terminates is going to be roughly equal to I over n. And then you can just plug this estimate back into the product we had to estimate the original probability, which goes as follows. So what you get is when you plug it back in, you're just going to be instead multiplying 1 minus I over n, because we looked at the complementary event. And when we multiply all these terms, this is like multiplying, very similar to multiplying the exponentials, because we know I is at most of order square root n, it's much smaller than n. And if we multiply with exponentials, we just end up summing these terms I over n, and it converges again to the same thing. So I think my y became an m, but it converges to the exponential of minus m squared over 2, which is again this Rayleigh law, and this n will cancel out. So this is a UST way, a UST proof of why you get convergence of the distance between two uniform points in the complete graph. You can actually just do a simple induction to iterate this, to take, for example, 3 points and get all the joint distribution of the tree spanning the first 3 points. And more generally, if you do it for k-steps, say, you can actually represent it in a nice picture, in the sense that you can run Wilson's algorithm and you can plot essentially an analog of stick breaking. So you can plot points so that the distance between any 2 points corresponds to the length of that branch, of the branch you just added in Wilson's algorithm. So here, for example, ln2 minus ln1 is the length of the second branch you add in Wilson's algorithm. And this I that was appearing in the formula we had before, it was equal to the current length of the loop erased trajectory. And this kind of gives you the heuristic that at any time you have roughly, in any time interval on the scale square root n, you have roughly probability, the length of where you are now, so the I is now a t, times the length of the interval to actually terminate the random walk you're looking at now, the loop erased random walk you're looking at now. And it tells you that these points actually converge in the scaling limit towards the Poisson process, which is exactly the Poisson process we use to sample the CRT. And this is one way of looking at the finite dimensional convergence of these uniform spanning trees. And it's exactly the statement I told you at the beginning, that if I take k uniform points in my uniform spanning tree, then the subtree spanned by these k points will converge to the equivalent subtree in the in the CRT. But of course, I gave you my statement for the torus and not just for the complete graph. So how would you extend this to the torus? So this was the proof, or this was a theorem proved actually about 20 years ago by Perez and Rebel, and they said exactly what I just said. You have this convergence of k-point functions. And the heuristic for why it's true is roughly that you could do the same kind of calculation I just showed you on the complete graph, but you could actually do it using segments. So this Laplacian random walk formula, you could also iterate it to get the law of a segment of the loop erased random walk. And if you could take some kind of segment length, which is longer than the mixing time of the graph, but less than square root n, the scale we're interested in. So say you take some m, which is a lot less than square root n, but a lot bigger than t mix. So the mixing time is just the time you have to run a random walk for it to forget its initial position. Then you have some hope of running the same kind of argument, but using segments of random walk. And the fact that these segments are longer than the mixing time mean that actually you have the various symmetries you need to do the same kind of calculation, because in the calculation, we just said that if we run one step of a random walk, the next step will be roughly uniform in the graph. And then we looked at these hitting probabilities, the probability that I hit one step before another. And again, if you know your random walk is mixed, you have the same kind of heuristics. And when can you do this? Well, you can, the mixing time for the torus is just the side length squared. So you can do this exactly when D is strictly bigger than 4. You really have a gap there. So that's a heuristic for why it's true. It's actually not exactly how they proved it. So what they actually did to prove it was they took the result on the complete graph, which was known, and they did some kind of coupling between Wilson's algorithm on the complete graph and Wilson's algorithm on the torus. And very roughly, it went as follows. So since they're interested in paths of length square root n, they took a random walk path of length square root n on the torus, and they divided it up into segments of some length, a bit like this. And they wanted the length of this segment to be m. And again, they wanted exactly the same thing, that m is a lot less than square root n, but a lot more than the mixing time of the graph. And of course, here I've just drawn some macroscopic loops, but of course also the random walk is making lots of small loops over time. And if you label these intervals, say I1, I2, up until the end, what you can show is that because the length of these intervals is more than the mixing time, the probability that two intervals intersect is roughly, up to constants, the number of pairs of points in the two intervals, so that would be m squared, times the probability that two random walks are at the same point at some time. So that's 1 over n, because they have, if they're independent, it's just 1 over n. Or at least, in fact, this tells you the expected number of intersections between them, roughly. And this is a good bound for the probability, because you're unlikely to have more than one intersection between any two intervals. It's a lot rarer. It's already a bit rare to have one intersection, and it's a lot rarer to have at least two intersections. So somehow the expected number of intersections will give you a good heuristic for what this probability is. And if you compare this on the complete graph, say on KL, and you just run a random walk, of course, you know that the probability that one step of a random walk is equal to the next step, unless I and j are adjacent, is just equal to 1 over L, pretty much. And so what they did is they wanted to look at this random walk trajectory, but kind of in a coarse-grained sense. So they wanted to just look at these intervals, and in some sense, look at the random walk obtained by just looking at intersections of these intervals. And what I just told you is a heuristic to say that the random walk you get looks like the random walk between 2 points on the complete graph, run for the same amount of time. And so this tells you that if I take the red distance, well, firstly, it looks like a bit like a random walk on the complete graph, provided I match these probabilities. And so that means I have to take L equal to n over m squared. And that means that if I take the red distance and I divide by the square root of L, which is square root of n times m, then this should converge to the same kind of distance in the CRT, because we know what happens on the complete graph. But then we also just know that the red distance should be roughly equal to the blue distance divided by m, at least up to constants. So maybe it's a bit full. The blue distance divided by m, so we get the distance divided by square root n. And so this is the heuristic for what they did to prove that this Wilson's algorithm on On the torus, it converges to actually the same thing on the CRT. They really couple things in this way. And of course, you have to rigorously argue why the distance are comparable. I mean, you have to put a constant in here because you have lots of little loops which you're losing. But actually, the length of the loop erasure is comparable to the length of the random walk because of what we said in the beginning about dimension 4 and strictly above dimension 4 means there are not many intersections. And there's also some constant also which goes in here, which changes all the constants. So you have a different constant here. But this is basically the idea behind that proof. Okay, so that's the finite dimensional convergence. And as I said, this has been known for 20 years or so. And what we wanted to do, look up was GHP convergence. And the first thing you can ask is actually, does this imply GHP convergence, like that I defined in the beginning with this, this isometric embedding? And it's not hard to see that it doesn't, because this kind of statement doesn't really differentiate in the limit between spaces where you add extra sticks of zero measure. So I could take my CRT, I could add an extra stick of zero measure. Of course, these two spaces have some real Hausdorff distance between them, so you cannot have convergence with respect to the Hausdorff distance. But this kind of difference won't be picked up by this type of convergence. And so what we did with the Safar-Matan is that we close the gap to prove this, or to strengthen this finite dimensional convergence. It's called Gromov-Weak convergence to this GHP convergence. And it's actually very nice to do this with Anita because we also used one of her results to do that. And so this is the theorem that we proved, and it's called the lower mass bound. It's a result by Anita and her co-authors from 2015. And what does it say? It basically rules out the picture that I just showed you. So it gives you some universal lower bound on volumes of balls in your graph sequence. So what you need to show is that for any radius on the right scale. So here I've put everything on the right scale because I'm rescaling my graph. So of course, if you have a different sequence, you have to have a different scaling. But you take any volume of radius of a ball of radius c on the right scale, and you need to show that there's some universal lower bound for the volumes of these balls. Because in the limit, this means that you cannot have a stick of zero measure appearing, essentially. And once you have this, this result of Anita and her co-authors, it tells you that actually this Gromov-Weak convergence we had before, which was the K-point convergence, plus this mass condition, it actually gives us the GHP convergence of the trees. So now I will just tell you briefly about how we proved this lower mass bound. And it's a priori, it's quite a hard bound to prove, or at least there are a few annoying things about this bound. Firstly, because it's global. So you really have to bound the smallest ball of this radius in the graph. And also in the UST, there are lots of correlations between different volumes, which means you cannot apply union bounds. Or for example, if you want to prove the same thing for Gorton-Watson trees, you can decompose the space into essentially independent parts and apply some kind of union bound, whereas you cannot do this for uniform spanning trees. So we did it roughly in 3 steps. And the first step was to overcome this global property. So we had some kind of bootstrap technique, which reduced this global aspect of the bound. And we showed that it's sufficient to prove a nice local bound. So if I just take a typical V, say V uniform in the torus, I can just prove it for this V. And in order to actually prove this local bound, there are 2 main steps. So one is you have to take some kind of spine from V and take a spine to the origin, say. And you want to show that it has a nice embedding in the torus. What do I mean by that? So it's actually called, the quantity we want to look at is called capacity, which I won't talk about too much, but I think Anita might talk about it a bit. And it means roughly that this black line from V to the origin is quite well spread in the torus, and it's quite hittable by a random walk. So the kind of structure you would want to rule out is, say, like a spiral, because if this black line was a spiral, then, for example, the bits in the middle, it would be very hard to have subtrees attached and to really gain some volume. So you want to rule out things like that, and so you have to add a step proving that these kind of events do not happen. But once you know that this spine is well behaved, so it's fairly well spread out and hittable by a random walk, you just take your point V and you look at all the points on this spine which are close to V, so within distance, say half of this radius from V. And you look at all the subtrees which are attached to the spine around V, and you show that the first generations of these subtrees give you enough volume to give you a lower bound on this ball, on the volume of this ball. So those were the 3 main steps. And I want to talk mainly about the 3rd step because it's more of a UST type argument. So just quickly, the first step, we use the bootstrap argument, which actually works for any kind of graph, not specifically for the torus or USTs. The second step, we used capacity arguments, so it's about random walks. And the third step I'll talk about now. And so the first step is actually, what is this local bound I said? So I said I could reduce the global bound to the local bound. There is a cost to doing that. So what's good about this one now is that it's local. But now we have to prove it for all R in some interval. And the scale we have to go down to is much less than the original scale. So originally I just had R equal to C square root n. And we have to have good enough tail decay on these kind of bad events we want to rule out. And so actually just a comment, I wrote it like this, but actually what we really proved was much better tail decay. We got exponential minus the log of epsilon to the -1 squared. And if you improve what you get here, you can also improve what you put as your lower bound here. And so actually we didn't have to prove it all the way down to n to the quarter. We were able to just prove it down to n to the half minus delta, where we could make delta as small as we like. But in general, you would need something like this. You can play with it a bit, but you need something like this. And you can play with it as long as you have, as long as you have a little o of epsilon here, you can play with it to try and get a different bound here. And then, okay, once we had that, we needed to prove this statement. So we needed a bound on this kind of probability. And how did we do that? So it's kind of what I just outlined roughly. You take your point V, and you take this nice spine gamma to the origin, which we will assume is nice. And I will just, by the way, I will just prove the case to avoid thinking about constants. I will just prove the case where C equals 2, because then you can just go distance R in this direction. And in principle, you can go distance R in the vertical direction, and all the vertices you catch there will be in your ball. And so anyway, you take a prefix of length R of this spine, and you divide it up into intervals of equal length, say epsilon to the half R. Actually, if you know what capacity is, it's a bit more natural to divide it up according to capacity, but this has the same kind of idea. So we'll just talk about length today. And then you let xi denote the number of vertices which are attached directly to the ith interval by a short path. And actually, the reason we make this shorter, so we could go all the way up to R, the reason we make this shorter than necessary is to control some kind of second moment. And then what you want to say is, okay, if I just look at what happens around one of these intervals, because I tuned my epsilons correctly, the expectation of the volume attached to one interval is roughly what I want. And the second moment is not too big. So I can run a second moment argument. And then you want to somehow say the probability that actually you test all the intervals and all the intervals have small volume is very small. So I will explain a bit where these moment estimates come from. And they come again from Wilson's algorithm. So for the first one, it's a lower bound on the expectation. So just to remind you, we had some path from V going down to the origin. And then we want to know, we have some interval here. We want to know the expected number of vertices, U, which are attached to this interval via a short path. And so if you take the expectation of this X, let's say this is X1, you just look at the sum over U, the probability that this U contributes to X1, so this event happens. And so what it means is by Wilson's algorithm, we know that, we know we've conditioned on this spine to be in the UST. And we know that if we then want to sample the path from U to this spine, we just run a random walk until it hits the spine and we loop erase it. And so it means that the probability that this event happens is lower bounded by the probability that a random walk started at U, it hits the spine in this time, and it hits the spine specifically in the right interval that we want. And of course, because we're summing over U, this is just like the probability when we start from a uniform vertex up to a factor of n. And the fact that we're conditioning on really hitting the spine at this right interval, it's actually enough up to constants to just consider the event that we hit this interval, because it's already quite a rare event starting from a uniform point that we hit this interval A1. And it would be even rarer to hit them both and to hit the spine first. You'd have to do something like you go around and you come back and hit A1, and it's even rarer. So this is a negligible event compared to just hitting A1 directly. And so it means that up to various constants, the probability is just given by this expression. And if you want to know what's the probability that a random walk started from a uniform vertex hits the interval AI in some time, actually by union bound, you just know that it's less than the number of chances you have to hit the set times the size of the set, divided by the probability at each time, so the uniform measure, because, okay, this is the stationary measure of the set. And actually the uniform bound is also a lower bound up. Sorry, the union bound up to constant is also a lower bound up for these events because they're also quite rare events. And so the heuristic is that this is the order of this sum, and so it's also a lower bound on the expectation. You can also get an upper bound on the expectation, and this is a bit more annoying because if you want to get an upper bound, this inclusion, the fact that we replaced the loop erased random walk with a random walk, it doesn't work actually. However, actually, it's not too hard to get around because it turns out that if you just replace, you can essentially replace a loop erased random walk by a random walk, and you just have to add this factor 2 and some constant here, because we know that actually, typically, loop erased random walks are of the same length as a random walk. So you actually can pass between the two. And basically the statement you need to prove is that given the loop erasure, with a decent probability, the random walk it came from is not too much longer. It's not longer than this constant times this length. And then you can just pass between this and the expectation. And then it's exactly the same calculation for an upper bound. And so you get that actually you also have an upper bound of the same order for this expectation. And the same kind of heuristic can be used to upper bound the second moment, because we're doing the same kind of thing. It's just if you're looking at a second moment, you want to look at the sum over all U and W, probability that they both are members of this, or contributing to this event Xi, or the volume of Xi. And it's the same kind of idea. So here we do the same thing. We take our V and our gamma, and we first want to ask if U is contributing to this event. So it's the same calculation we did before. And then we take another W, and again, we can treat W like a uniform point because we're summing over all W. And now, if W is also contributing to this event, there are two options. Either my random walk from W leaves W and its loop erasure hits, it hits the same interval, but with a short loop erasure. Or it can now also join directly onto this branch we created by adding U in the first place. And this is actually the reason I didn't go up too high when I looked at my other direction, because the length of the path between this interval and U is of the same order as the length of this interval we originally considered. It means I essentially only multiply probabilities by 2 by adding this branch on average, or a constant. And so it means that this second moment is just the same, this second term that we get once we condition on U really contributing. This is up to a constant, the same as if we didn't have this path. And we get that the second moment is upper bounded by something which is like the first moment squared. And this means that you can run a second moment argument on a single interval to say that with a positive probability, your contribution from a single interval will be large enough to prove this lower mass bound. And then what you would ideally like to do is then just test all of the intervals one by one, and say the probability that all of these intervals fail is just the probability that one fails to the power of the number of intervals. And of course, you can't directly do that because these intervals are not, these Xi's are not independent, right? So you can't just multiply the probabilities. But there is some lucky chance, which is that the UST has what we call negative correlations. So if I know that if I know that X1 is big, it's likely actually that X2 is a bit smaller than average and vice versa. But unfortunately for us, this is only known at the level of expectations. It's not known really in terms of events. So it means that you still cannot directly deal with this product or deduce this product as an upper bound for the probability, because you don't have an upper bound on the second moment once you condition on the first one failing. It's in the wrong direction. It's in the correct direction for the first moment, but the wrong direction for the second moment. And so we had to do something else. And I will just tell you quickly because I haven't got lots of time. There's some good news, which is, okay, everything's good for the first moment, but it's bad for the second moment. And we don't really want to condition on what really happens. Say we have our V, our gamma, and we condition on all the stuff that's attached to V. And then we take a W and we ask whether it might be, so this is my second interval, whether it might be connected to the second interval. We don't really want to condition on all these red subtrees directly because now we've just completely changed the graph. And if my random walk from W is doing the right thing, it has to really go on an annoying graph and avoid all these branches that are already constructed. And we don't really want to deal with this. So instead, what we did is we added a new vertex to the graph, which we called the sun. And basically it allows us to kill random walks. And what you do is you add this vertex, you add an edge between this sun and every other vertex on the graph with a very small weight, so that a random walk will always jump there with probability 1 over this length we're interested in. So it means typically you run random walks for the time epsilon to the half r, which is the time scale we're interested in, but not much longer. And this is good because it gives us a way to upper bound the second moment. And it also doesn't reduce the first moment by very much. It only reduces the first moment by a constant factor because we only counted random walks really that arrive at x1 in this time. So if you know you kill random walks after this time, typically you're just multiplying probabilities by a constant factor. And so this actually, all these ingredients allowed us to write some kind of conditional probability, given that, say, x1 is small. We still have a lower bound on the expectation of x2 because we have the right domination and it's of the right order. But we also have an upper bound on the second moment of x2. I forgot to write the conditioning, but it's also true under the conditioning because we're killing our random walks anyway. And so this gives us an upper bound on this conditional probability. And then you really can multiply the probabilities and you get very good tail decay. And so yeah, I would say that's the fun part of the argument. The other ingredients are maybe more technical, so I didn't talk about them today. But I think that's my last slide. So I'll stop there and thank you very much for your attention.
Thank you very much, Ellie, for your very nice talk. Are there questions? So people, please feel free either to raise your hand or unmute yourself, or if you want to write in the chat, we can read out loud your question.
I guess I had a question, which is, do you know what happens in dimensions 2 and 3?
Yep. So
dimension 1 is maybe not so hard on the torus, but 2 and 3?
Yep. So in dimension 2 and 3, most results are written on the lattice instead, because you can actually also take local limits and work on the whole lattice. And in dimension 2, you're in this world of conformal geometry. So if you take, for example, this kind of piano curve, so it's the contour curve of the UST. This converges to an SLE8 curve. This is the result of and also it's known that a single branch, which is a loop erased random walk, it converges to SLE2. This is a result of Lawler, I think. And also in a different direction in dimension 2, there are some results of Barlow, Croydon, and Kumagai, and they showed some kind of tightness. If you take actually the uniform spanning tree of the whole space, which is defined as a local limit, you can rescale this sequence. So you take the uniform spanning tree along with its embedding actually, and they proved tightness of these spaces. So that's dimension 2. And then more recently, they did the same thing in dimension 3. So they proved tightness. I mean, they also proved more. They proved what, like the Hausdorff dimension. In dimension 2, they know exactly what the Hausdorff dimension of any limiting tree would be. In dimension 3, they do know, but this dimension is not explicit because it's a function of the loop erased random walk growth exponent, which is known to exist, but it's not known exactly what its value is. There are bounds on it though. And really in each step, or for both of these cases, they use the connections between loop erased random walks and uniform spanning trees. So the results really come from transferring results for loop erased random walks to results for uniform spanning trees.
Okay, thanks.
Andrei, please, I think you can unmute yourself.
Yes, thanks. Thanks for a nice presentation. Just one question. You point naturally to toruses as a special case. What is here the difference between the analysis on random graphs and the torus is a special case? Thanks.
Yeah, actually, our result is more general than just for the torus. I just stated it for the torus, but I can tell you what we need as our result. So for technical reasons, we need, so what we do is we take a sequence of graphs, and GN has size n roughly. And for technical reasons, which is mainly because it was in this result of Perez and Ravel, we need it to be a transitive graph, vertex transitive. We also need this condition. So if you take up until times square root n, you take t, pt, okay, is transitive, so you can take any vertex here. We need that this is bounded uniformly, such for all the n. So, and why do we need this? This is because actually this gives you an upper bound if you want to look how you pass between random walks, or rather how you pass between loop erased random walks and random walks. And so I tell you this is my loop erasure, and I ask you what was the random walk it came from. If I want to know kind of the length of the loop attached at a certain point, actually this is an upper bound for the expectation of the loop, because this is just giving me return probabilities for a random walk. And so this enables us to pass between lengths of random walks and their loop erasure only by using a constant factor. And then the third thing we need, and actually someone recently told me that maybe there are some recent results saying that this is a consequence of the second thing, but for now it's a separate assumption, is that we need the mixing time. So again, I need something like that. Is this alpha positive, such that the mixing time is really less than square root n by this polynomial factor for. So actually that was our result, but later with Matan we proved a different result, which is you can take random graphs where you don't have this transitivity assumption, but we needed them to be dense. And so if you have a sequence of dense graphs converging to a graphon and connected, they need to be connected. You can also play the same game, and then you don't need, so most of these results you get for free from the fact that they're dense and they converge, actually. And actually in this case, it's nice because you can actually extract the constant from the limiting graphon. Whereas I think Anita might talk a bit about the constant in her talk, but in the case of the torus, the constant's written in terms of random walk intersection probabilities and various things like that. And it's a bit less explicit. Well, it is explicit, it's just a bit less of a nice formula. Let's see.
Okay, thank you. Thanks.
Thank you. May I ask one quick one? Maybe it's very naive. So the reason why you need that mixing time to be less than n square root of n minus something. So is it because of your rescaling by square root of n?
Yes, yeah, basically, and because, for example, when I explained this coupling of Perez and Ravel, so they took a random walk of length. Okay, so we hope that the natural scale should be square root of n if the same result is true. And they did this, they divided it up into intervals, and we needed somehow each interval to be independent of the previous interval. And because I wrote something like the probability that I intersects ij is equal to the size squared divided by n. So it's the fact that these intervals can be more than the mixing time, longer than the mixing time, it really gives you the necessary independence to do the coupling and treat them as like independent, or like steps of an independent random walk on a large scale.
Yeah, I see. Thank you. Yeah. So it's not true that maybe you can imagine just that if the sequence of graphs is somehow different, then maybe you need a different rescaling for.
In lower dimensions, you'll need a different rescaling. So in lower dimensions, the paths will be longer than square root n if n is the number of vertices. And so, I mean, in some sense, the square root n is coming from the fact that you can do this coupling that really random walks or like liberalized random walks, and it's coming from the fact that it's correct for the complete graph. And then when you start to feel the dimension, that's really when somehow it takes you longer to really arrive or something, and or Yeah, and the scaling is different. So in dimension 2 and 3, the scaling is different. For example, in dimension 4, it should be square root n, but there's a log factor, which comes from the fact that dimension 4 is critical. But the scaling limit should still be the CRT actually in dimension 4, but it's only proved in this finite dimensional sense.
I see. Yeah. Meaning that you still miss some like convergence of global quantities, right?
Yeah, so it's known this thing, if you sample k points, the result of Jason-Schweinsberg, if you sample k points in the UST and you rescale by this factor, it converges to the equivalent thing in the UST. But what we don't know is that this mass bound is true. So we can't rule out that in the limit, there might be some extra small sticks or sticks of zero measure, which appear in the limit, basically.
Okay, thank you very much. Are there other questions? If they're quick, maybe we can still have them. Otherwise, I think we can just maybe thank Ellie again for your very nice talk. Thank you very much. And we can switch to Anita's slides as well, in order not to be too late. And in any case, we can always have more questions at the very end.
One second, I'm
Yes.
trying to open.
Okay, good. So maybe I think we can start again, right? So, okay, welcome back. It's a pleasure to introduce the second speaker of this session of the One More Probability seminar, which is Anita Winter from the University of Duisburg-Essen. And Anita will talk about scaling limit of the Aldous-Broder chain on regular graphs, and in particular, the transient regime. So please, Anita, you can start.
So thank you, Luisa and Roger, for this kind invitation to give the seminar here. Thank you also for teaming me up with Ellie, because I think it's a really neat fit in topics. Today, I'm talking about the scaling limit of the Aldous-Broder chain. This is joint work with Osvaldo Antuncio Hernandez, whom I already saw in the audience, and Gabriel Batsunza Ojeda. Let me start simple by just recalling what is the uniform spanning tree, which is an object we have in common. So given a finite simple connected graph, a spanning tree is nothing else than a subgraph which uses all the vertices, but not necessarily all the edges, and which is a tree in the sense that there are no loops. The uniform spanning tree is the uniform distribution on the space of all the spanning trees of a given graph. There is a nice connection between Markov chains on graphs and random rooted spanning trees. In fact, you can use Markov chains in order to generate random rooted spanning trees. And here is how it could work. Namely, assume that you have given the graph and you have given a rooted spanning tree. Think of the root as the position of your Markov chain. Then the Markov chain does a jump according to some transition probability. It has two possibilities. Either it uses an edge which is already in the spanning tree, or it does not. In the first case, nothing really is happening except that the position of the root is changing according to the position of the Markov chain. While if you are using an edge which is not in the spanning tree, then you are putting an edge between the old position and the new position. This way you are creating a loop, which you don't want because you want to generate trees, so you have to take away one edge from the loop. And the rule says that the edge which you're having to take away is the edge from the new position of the root in the loop, the first edge in that loop, which is pointing towards the old position of the root. Or with other words, you're looking for the last time you have been in the new position of the root and look what you did one step further. And this edge is what you are taking away. And this gives clearly a dynamic on the space of rooted spanning trees, which will be the Aldous-Broder chain. To motivate it a bit, why we are looking at that, let me remind you that there's a close connection between spanning trees and stationary distributions of Markov chain. In fact, if you have a reducible graph and a Markov chain on it with transition matrix P, then you can write down an explicit formula of the stationary distribution in terms of spanning trees, rooted spanning trees. If you would like to know what is pi of rho is a vertex in the graph, then you just sum over all the spanning trees which are rooted at rho. And what you are summing are weights on the tree, and weights are defined to be the product over all the edges you have, and the edge weights. And an edge weight is the transition probability from U to V. If UV is an oriented edge in the spanning tree where the orientation is always pointing towards the root. The point is, if you would like to understand this formula and would give like a 2-line proof, this is something I learned from Aldo's paper from the 1990, where he came up with his algorithm. Then you can argue as follows. Let's assume your random walk started at time minus infinity, together with a rooted tree, and you do what I just said, that each time you are moving your Markov chain, you're also changing the tree a bit, and you let it run until time 0, then you are clearly in the stationary distribution for the position of the Markov chain, but also for the tree. And you can also read off the tree at time 0 by just looking a little bit back in the past. And the way you're doing this is that you know every vertex must be connected by an edge in a spanning tree. So you just take the union of all the edges from V to the position you had the last time you had been in V one step further. So if you're collecting all these edges, then I clearly get a spanning tree, and I can also ask for the distribution of the tree I get and the probability that I get a tree T, and the root position will be rho. It's very easy to see, must be proportional to the product of all the edges in the spanning tree, the probability that your Markov chain went from V to the parent of V, where the parent of V is the vertex not pointing towards the root. And if we now sum over all the spanning trees which are rooted in rho, then you get the formula for the stationary distribution. So this was a very neat argument you find in Aldo's paper, which he used actually by working with the time reverse Markov chain to come up with an algorithm to generate the uniform spanning tree. In our case, we get usually a more arbitrary distribution, but of course, we can also work with this forward Markov chain by just taking regular graphs and not just a Markov chain, but a simple random walk, which jumps from any vertex in any of the possible directions. Then the transition probabilities are just 1 over the degree of that vertex. And if it's a regular graph, then you find that you must get the uniform distribution, the uniform spanning tree as the invariant distribution of this tree-valued stochastic process. And this is what I would refer to as the Aldo's border chain towards the talk. I would also do another modification. I don't want to start necessarily in the full tree. I can start in any tree. And in particular, I would like to start in the trivial rooted tree, which consists just of one point, which is the position of your random walk. And now the random walk keeps going. And each time it goes and sees a new vertex, it just draws a line, adds a line and this vertex. And this way, your tree is growing. In the moment, it's just a line segment, which is embedded into space. But here you see, if you trace back, you are kind of closing a loop. So you have to apply this Aldo's border rule, taking away an edge and adding this edge. But of course, since it's the same edge, you don't see the changes. And you have to wait until you maybe produce a longer loop to see it. So now if the random walk goes up, we are closing a loop. We do the Aldo's border. If we are going up again, we will see the Aldo's border algorithm taking away, adding an edge and taking away an edge. And my random walk is performing this. And while the random walk is walking, the tree is growing and also rearranging and becomes more and more tree-like. Okay. So what I would like to do in today's talk is I would like to talk about scaling limits of this tree-valued dynamics, as underlying graphs tend to infinity. And I would also like to use the notation G for the Aldo's border chain if we work on a particular graph G. To get started, very similar to what Ellie did, but slightly different. That's why I'm telling you. I will talk about how I think about trees. For me, trees are metric spaces. I have vertices, I have mutual distances between the vertices. And I would also like to work with a Gromov-like notion of convergence. And what is typical for Gromov is that you have to deal with metric spaces. And in order to measure the distance or to talk about convergence, you usually embed them in a common metric space. No? And thanks to Ellie, I could use a picture. So you might see the similarities. But now I'm not just evaluating the distance with the Hausdorff distance and the Prorochow distance, but just with the Hausdorff distance. And for those of you who don't know, Hausdorff distance is always a distance between any two closed subsets of a common compact metric space. And the way it's defined is you look for the smallest epsilon, such that if you blow up your sets by epsilon, they just cover one set, the blow up of one set is covering the other. It's defined in a symmetric way. Okay, so this is my notion of convergence. That's the slide we have all seen. In Ellie's talk, it's the famous Aldous result on the scaling limit of branching trees. Assume you are having a branching process or the family tree of a branching process. The offspring distribution is critical, has finite variance. Condition the tree on having exactly n nodes. Then if you rescale edge lengths by 1 over square root of n, or more precisely by 1 over square root of sigma square n, then it will converge weakly with respect to this Gromov-Hausdorff notion of convergence towards a random compact metric space, which in the literature is called the continuum random tree. And that's precisely Ellie's Brownian continuum random tree. It has different names because you can also represent it as the tree below a Brownian excursion. Something also mentioned by Ellie is if we are on the most simple graph, the graph without geometries, the complete graph, then the uniform spanning tree is nothing else than the uniform tree, and therefore it's a particular branching tree, namely with Poisson offspring distribution, and Aldous theorem applies. We can rescale edge lengths by 1 over the square root of the volume, and we will converge to do the CRT. There's one thing we did about 20 years ago together with Steve Evans and Jim Pittman is that we were not just rescaling the uniform tree on the complete graph, but the Aldous-Broder chain, which I just introduced to you. And the result we found at that time reads as follows. If I have a sequence of Aldous-Broder chains on the complete graph, if I start in the trivial tree, if I speed up time with the square root of the volume, if I rescale edge lengths by the square root of the volume, then I will converge weakly in the score hot space towards a Markov process. And this Markov process is called the root growth with regrafting. It is a piecewise deterministic Markov jump process. And the dynamics can be summarized as follows. Assume that we are currently in the metric or pointed metric space TD rho. Then we have on the one hand regrafting, on the other hand root growth. Regrafting would mean that for any point in the tree, at a unit rate, a cut point falls down. And if this cut point falls down, then the tree just decomposes in two parts. One part contains the root, the other one not. And the one which does not contain the root, let's say it's a subtree above this cut point, will fall down to the ground. The cut point and the root, they will glue together and they will keep doing stuff together. They will be identified. And in addition, between any two regraphed events, you have root growth. So the root will start growing deterministically with speed 1. A point I would like to make use of today is that you can construct the root growth with regrafting process by a driving point process, a Poisson point process. And the way we are doing this is very similar to the stick breaking construction, which was explained by Ellie. You take here not just the Poisson point process with inhomogeneous rate R, dr on the line, but instead you take the Poisson point process with unit rate on the triangle in the upper half plane. And then once you have points below this triangle, they have two coordinates. The first coordinate for you, it's always the time at which the regrafting happens. The second one is telling you which of the points in the tree you have grown so far will be the cut point. Where will the cut happen? And the best to explain the construction is to show you a nice movie which was produced by Osvaldo, which explains it just for 2 points, but it's very neat to see. So the idea is, in the very beginning, we have root growth. No? The root is growing until time tau 1, producing a segment of length tau 1. Then the cut point falls down precisely at the position of U1. The subtree above falls down, glued together, the root kept growing. No? So now we'll have a second cut point falling down. You know from the U2 where it will happen. The subtree falls down. It glues together, no, the root keeps growing. This is how the root grows with regrafting limiting process works. Good. So this is what we showed on the complete graph, and there are many reasons, as explained by Ellie, to wonder whether there are other graphs for which you can prove similar results. And in fact, it was conjectured by Pittman that for sure it should be possible if you look at high-dimensional tori or fast mixing graphs. And we have heard about the result by Perez and Revel, and also by Ellie and Asaf and Matan Shalev. There is a result in D = 4 as well, which is by Jason Swainsberg. But because the question came also by Roger in the first part, you can do this also for dense graphs. If I have a sequence of dense graphs which converging in the graphon sense, then there's also a nice result by Ellie and co-author, Matan Shalev. In more detail, we have seen this already. If I have the torus, let's say I'm in dimension d larger or equal than 5. We have seen Perez and Revel result basically saying we scale edge length by the square root of the volume of the torus. N is the side length of the torus, the volume is n to the d. And Schweinsberg showed that you get a similar result. Okay, let's look back to Perez and Revel. You have this constant beta. It was also there in Ellie's talk. That's a constant which depends on the dimension of the torus, of course. So in d = 2, you don't find such a constant, but you can as well write a statement if you do a little bit of a logarithmic correction of the square root of the volume and rescale edge length by n square log n to the power of 1/6. Then there's the result, we have heard about an hour ago, which actually strengthens the topology, the notion of convergence in which this happens. And this is very nice for us because the result we have seen in the first talk implies the Gromov-Hausdorff convergence for the rescaled uniform spanning T towards a multiple of the CRT. And this tells me something about the spatial scale because this is kind of the one-dimensional distribution, which will converge for my dynamics if I know that I rescale by 1 over the square root of the volume, at least on the torus. And here is our main result stated first just for the high-dimensional torus because it's easier to read. If I have a sequence of Aldous-Broder chains on the high-dimensional torus, let's say d larger or equal 5, starting in the trivial tree, then I will find constants beta of d, alpha of d, both positive, both depending on the dimension, such that, again, if I speed up time by the square root of the volume, I rescale edge length by the square root of the volume, I will have convergence on the level of processes, weak convergence in the score hot space, with respect to Gromov-Hausdorff convergence towards the root growth with regrafting. Up to that I need to do a time change by a constant factor square root of alpha of d, and I have to rescale edge lengths or multiply edge lengths by beta of d. And this is a nice result we have talked about, at least in the one-dimensional sense, an hour ago, but let's just look at it a little bit. Then you will see that on the left-hand side, you have a geometric object. On the right-hand side, the object is clearly not geometric. And the reason is that we have some averaging out of the geometry is that on the high-dimensional torus, you can kind of clearly separate between short and long loops. If I start with one point, then I will, of course, run into my path, create short loops for a while. That is fine. But once I have moved my path, let's say the mixing time, when I'm almost in the uniform distribution on the torus, then hitting, let's say, the root where I started will be just by pure chance. No geometry will help me here. This will be pure chance. And these are the things which happen on macroscopic scale. If things happen by pure chance, I can not choose my time scale in such a way that I will see like a Poisson number of these events, a Poisson number of re-rafting events, let's say. Okay, and in order to prove this result, it is very common to not necessarily work with the process itself, because Aldous border chain, it's very, very difficult. It's kind of a beast if you would like to track it and see what it does. So what you do is usually you simplify your process. And if you simplify, you have to try to do two things simultaneously. It's like a trade-off. You have to do it in a way that the simplified object is really simpler. It has nice properties, but on the other hand, it should still be very close to the object you would like to look at, so that after microscopically rescaling, you don't see the difference of them. And this is the hardcore point, and the hard argument in the proof is coming up with such a process, which is much simpler to study, but very close. In order to explain this, let me remind the objects we had. The first one, gamma, and the following should be just a pass. A pass can have loops. And we have loop erased random walk, which will play a role. The loop erased pass here, exactly as in Ellie's talk, should be the one where we erase the loops in chronological order as they appear. And it will be there, of course, because we know that the uniform spanning tree in between two branch points is just a loop erased version of the random walk. So loop erasure takes away the loops. You see this dotted loop, and it results always in a path which has no loops in comparison to gamma. And the third object is the Aldous Broder driven by gamma, by a path. And Aldous Broder driven by gamma, you see it in the middle piece. As soon as the loop is closing, you take away one edge, just one small dotted edge, because you would like to keep it a tree, and then you keep on going, and you see each time you're closing a loop, you're actually branching, so that you grow more and more in the tree structure. And the key idea in our simplification is, why not ignoring at least short loops which are shorter than a macroscopic scale? That's a very nice and neat idea. It has only one problem, because if you do it too greedy, then you might just disconnect into several components. So you have to be a bit careful. But the key idea, erase the short loops, call these short loops, let's say these dotted things, ghosts. And whenever your process run into a ghost, that's a feature of a ghost, you don't see the ghost. You just pretend you have not been there and keep doing what you would do if you have not been there. But be careful in erasing too many loops. And this being careful leads to the right technical definition of a ghost set. The ghost sets are something which depend on what I understand under a short loop. I fix an S. Short loop is for me a loop which is no longer than S. And I define my ghost sets recursively. Ghost sets are always growing. In the very beginning, there are no ghosts. And if I know what are the ghosts at time n-1, and I would like to know what are the ghosts at time n, then I'm adding all the indices m, which are no more than s in the past from the perspective of n, such that m is not the ghost itself and satisfies two conditions. The first condition is that it should be inside a loop shorter than s, which is closing exactly at time n. And the other one should be, and that's the technical one, that there is no twist with another loop. And this no twist condition, it's drawn here by this picture or illustrated in a nice way. So I don't know, do you see my pointer? Good, no? So you start here, you go all this way, you close this long loop, you are here, and all of a sudden you will close a short loop. No, by the way, this kind of picture, I call it twist. Osvaldo likes to call it pretzel, and I think it has a bit of the shape as well. So what's happening here is at time k1, you're opening the long loop. The long loop would stop here at time k2. But before you actually completing the long loop, you have started to open a short loop. at time m1, which is closing at time m2. And whenever you have such a constellation, it's not good. Don't erase the small loop because your graph will disconnect into two components. No? So in that case, we have to do something else. I am showing you what we are going to do by telling you what is the simplified process. So once I have these ghost these ghost sets, I'm introducing my new process for any time n as being the subgraph of the Altos-Broda of n, which is spent by the non-ghost in time indices. No, I just don't look at the ghost indices. And this might look as follows. You see here the two evolving in parallel. On the left, you will see the Altos-Broda, on the right, the skeleton. No, as long as there are no loops, you do, of course, always the same. There is nothing to worry about. But now, I have this backtracking. And backtracking, this was actually a loop of length 2. No, you have one vertex which becomes a ghost. You have another one which becomes a ghost. So here you have two loops concatenated also. You keep going. There was another small loop here, no, which all of a sudden turns into a ghost loop. Then we have this, if I go up, I will have a loop of size 6, and let's say 6 for me, it's already too large, and I don't erase it, no, because my S was, let's say, 4 or 5. Then I have the stick. I will go here. I will turn to the left, but now let's go back. Now, because if I turn left, no, I don't see that I have been there before, because for me it's just a ghost, so I will draw the edge. But when I come back, it will be a ghost again. I'm closing the loop, and so on. No, I keep going. So you see here on the left, the Altos-Broda, on the right, the skeleton chain. And the way we have defined our ghost sets is that we can prove that the skeleton chain at any time n gives us a connected subgraph and therefore a subtree of the Altos-Broda. So all we worry about in the moment is whether or not they are far away from Altos-Broda. But before explaining this to you, let's summarize the dynamics. The dynamics of the skeleton chain is root growth. No? If I see a new vertex, which I have not seen before, I will just add this vertex and I add the edge connecting this. If I go to the third one, the S ghost loop erasure, that means that if I'm closing a small loop of length shorter than S by running into the skeleton, and I have no twist with another one, so then I will clearly have my ghost sets increasing at that time. And in that case, I will just form a loop of ghosts, which I erase in the skeleton form. No, this will be my loop erasure. And then I have the middle part, which is the tricky part, because in this one, I will hit a vertex in the skeleton, so I will complete the loop, but there must be something going on. Either my loop is too large, I'm not erasing it, or there is a twist with another loop. Then I will also not erase it, and I will just do what I'm supposed to do the Altos-Broda move. Then I can't do anything wrong. That's the dynamics which the skeleton is following, which is producing us this picture. And the first question we want to see is that the skeleton is the distance of the skeleton tree to the Altos-Broda tree can be bounded in Hausdorff distance in a uniform way. And in order to do so, we cannot do this with any deterministic path gamma. We have to impose properties. These are properties which are usually satisfied with high probability for the random walk path on the graphs we are considering. But no, for the moment, I'm still looking at processes driven by deterministic paths, and I impose these conditions, and I call a path a good driving path with respect to some parameters n, r, s, s prime, which I made become a bit more clear later, and is always the time until which I would like to have the good path property. S is the size of being a small loop, R is the size of being a large loop, and the first property indeed say there are no loops of intermediate size. No, either my loops are smaller than S prime, or they are larger than or longer than R. This is the first property I would like to have. And if I have such a property, then In that dynamic, I have here this Aldous-Broda move, which comes with an index at which the Aldous-Broda move is performed. I can distinguish two cases. No? Either it's an Aldous-Broda move index because I'm closing a loop shorter than S, but I'm in twist. Then I call it the S Aldous-Broda move index. These are bad indices because I don't really know what's happening. Or I'm closing a long loop longer than R. These are nice ones because they are actually the one we will see on macroscopic scale in terms of regrafting. I have a second property, and this has to do with the fact that already in the small simulation I showed you, you saw that loops can be added. No? So I cannot say the error I do in a Hausdorff distance is at most S, because I can have a loop in a loop in a loop. No? And therefore I have to kind of cut it somehow and say stop. No, I cannot do more than this. And points which are helping are so-called cut points. A cut point is a point for which if I look at the range of the interval L minus S prime L, that means L is a cut point if I look back in the past S prime and forward in the future S prime, these two ranges do not intersect. This is for a random walk, maybe a rare event, in particular if I require my S prime to be large, but I am imposing this condition that any interval which has size S contains one cut point with respect to S prime. No, and apparently I can choose later S and S prime accordingly that my random walks will satisfy these on the graphs for which the result holds. These are two things for being a good pass. And there's another one. Here's the first consequence of this one. And in order to phrase this, let's look again what this skeleton is doing. I have three cases. The first picture shows you that I'm seeing a vertex which was not in the skeleton before, so the branch is just growing, the tree is growing, I have root growth. In the picture on the very right, I'm closing a small loop, shorter than S. So the branch gets a bit shorter. The tricky part is the one in the middle. Now, in the middle, I'm closing a loop, but oops, the closing point is a different branch. No? And this can be a large one, then I'm on macroscopic orders here regrafting. This can be also a very short loop. No? In this case, I better don't erase the loop because the skeleton will be disconnected. And the observation is that if I'm having good paths, then I can show that whenever an index is an S Aldous-Broda move index, such a bad index, short loop, but I'm still hitting another branch, then I must find no more than S back in the past, an index at which I have closed a long loop of length larger than R. So these bad indices, they are always very short after branch point. And this location will help me later for doing these estimations I would like to do. So I'm not having just good path property, I also have decomposable property, and this has to do with things Ellie has explained to us, which comes with the idea of how to prove these results. Namely, to take your random walk path or the timeline and decompose it into intervals of length R. No? Ellie called it M, I call it R, but the idea is that R is of much smaller order than the macroscopic order in which you rescale your edge lengths, and that you think about them as the points in the complete graph. And so I decompose this into segments, and I'm also mark some forbidden zones in red, which we call the buffer. I choose them of length 3s for a certain reason, and all the others I call the core of such a segment, the blue parts, and my decomposability properties are two. There's one which we have seen also in Ellie's talk, namely that we don't have triple intersections. If I have two segments for which the core parts intersect, then they will not intersect with the core part of a third one. None of them. And the second one is that these buffers are forbidden zones. That means the range of a buffer segment of such a red thing is disjoint from the range of any interval, provided that the interval is at least S apart. Now, of course, if it's the neighboring one, then you can hit, but we think about S usually as the mixing time. No? And if I'm the mixing time apart, then I will not hit this. And the key in the argument is that, of course, you choose S so small that until the macroscopic timescale with overwhelming probability for your random walk path, you will not see intersections which kind of involve the red parts. Just a matter of probabilities. And under these two assumptions, if I have such a decomposable path, we can show that the skeleton and the Aldous Broder for any time n until the time until which we are decomposable will be no larger than r. And if r is of smaller order than the macroscopic scale, that's fine. No? We can from now on just study the skeleton one. And the skeleton has already the features we saw in Ellie's talk. It has the root, the loop erasure, no? Because I'm growing or I'm erasing the loops. It just has these little bits of distortion of the long loops, Aldous Broder move. They are fine because we actually want the regraphed events. And it has these bad Aldous Broder indices, which only happen right after such a regraphed event. But most of the time, we have loop erasure. And this is basically the key argument. So to wrap everything up, what I can do is the following. I can introduce, I now would like to estimate the distance between the skeleton chain and the root cause with regrafting. No? And for that, I will do the following. I will introduce indicator functions which tell me whether the core of the J's segment intersects with the loop erased version of the core of the I's segment. Either yes or no. No, this indicator is 1 or 0. Such an intersection happens rarely. So in most of the cases, these Z variables will be 0, but sometimes they are 1. This is when we regraphed. And I will do exactly the same for my point process, which is driving the root cause with regrafting. Now I think about a nice and decomposable point process. Decomposability is defined very similar to what we had before. No? What I'm doing is I will discretize this triangle. All these little squares will get side length C. C is just fixed beforehand. And then I will just put an indicator on either such a square contains a point or not. And being decomposable basically means that you will not have two squares in the same row or on the same column where you have a point, and that also there's only one point in such a small C part in such a small square. So I have these two indicators, one coming from the driving random walk, one coming from the driving point process. And then we proved a very technical estimate, which was telling us, provided that these driving processes, the gamma and the P, they are both decomposable, and all these indicators agree until a certain level, then I can really have estimate the Gromov-Hausdorff distance between the skeleton chain where where edges have length A now, and the root goes with regrafting uniformly over time. And I can do this by certain expressions, which I, of course, don't expect you to be able to read. But what we later want, of course, is that this goes to 0. No? So let's see what is qualitatively there. We see that somehow there goes in the length of the loop erasure, which is compared with C. C is something deterministic how the root growth is growing. No? This will probably get small because we are able to show concentration inequality or concentration for the length of a loop erased path around the mean. And then we have C. C should go to 0, this edge length of the square. And we have the number of points we want to see. So we have to do the time scale in a way that we only see a finite number of regraphed events in a finite time interval. That's basically what you can read here. Other than this, I apologize for having such a detailed formula. It gets better now, I hope. No? So I have shown this, or we have shown this under the assumption that these indices are exactly the same. No? And the first thing we show is that we can couple the random walk and the Poisson point process such that we can control the probability that all these indices are the same. No? The only assumption we do is that, let's say for the first one, to have a point in the first square has the same probability that the second segment intersects with the loop erasure of the first in the core. No? And again, no, of course, you don't need to see all these explicit expressions, but I just want to show you what brings this close to 1. No? So we see, I start from the very end. No? We want C has to go down to 0. The length of the square, the approximation. That's fine, then this one will disappear. We want that R is of smaller order than the square root of the volume. This brings this one down. And last but not least, we will have here, the Q. The Q is everything holds as long as short means larger than Q times the mixing time. So if we choose for Q, let's say the logarithm of the mixing time, no, it's fair enough. This will go down to 0 also if the mixing time goes to infinity. So we have a good chance, no, to later show that this one goes to 1, this probability that they're all indices the same. Okay, and this tells us what I have shown you, how to choose our scales. How to choose the time scale? Well, the time scale has to be chosen such that it's R over C. No? And C has to be chosen such that these two probabilities for the indicators to be 1 are the same. No? And that basically boils down to saying that C square, C depends on R, is just a probability that a segment of length R intersects with the loop erased version of a independent random walk segment of length R. Time scale is R over C. We also know something about the edge lengths because the edge lengths are clearly the C over the mean length of a loop erased path. No? Having this concentration around the mean concentration phenomena proven, then we have to choose it like this, and we can state almost state our result. I would like to say, unfortunately, that I'm always struggle the same point where Ellie is struggling with dimension 5 and 4. No, I state everything in the transient case. In the transient case, we have the expected number of self-intersections. If I let run 2 independent random walks, start them in the same position, let them run until the mixing time. This I want to be in the lim soup as n tends to infinity for a sequence of graphs to be finite. No? I'm looking only at graphs, sequences, which are where the graphs are regular and where the mean number of intersections until the mixing time is finite. We are not imposing the transient, how did you call it? Transitivity. We just have regular graphs. That's why it depends on rho, but you can always take the supremum over all the vertices here. So one consequence of this transient regime is that if I have my sequences Rn for the length of the segments to be larger than the mixing time, to give it some room for our arguments, let's say logarithm of the mixing time squared, but smaller than the square root of the volume, then I can show that Rn over Cn, this was my time scale, is of the order of the square root of the volume. And I can also say that the factor with which I rescale the edge lengths are of the order of the square root of the volume. Also, I think it could be the inverse here. Let me, sorry, this is a typo on 23. The very last one should be of the order of 1 over the square root of the volume. No, good. And now we have everything we need in order to actually phrase the result. More general result. Now we assume the transient regime. We have a sequence of simple connected regular graphs such that the expected number of intersections for 2 independent random walks observed until the mixing time is uniformly bounded. And then we can say that if we have a sequence of Aldous-Broder chains on such a graph sequence starting in the trivial tree, and if we can choose our sequence Rn diverging such that it fits, is of larger order than the mixing time times the logarithm of the mixing time to the power of 2 and of smaller order than the scale at which we want to rescale the edge lengths, then I can state the result where I have to speed up time by Rn over this intersection probability or the square root of the intersection probability, and I have to rescale edge lengths by the square root of this intersection probabilities divided by the mean length of a loop erased random walk segment of length Rn. And this will converge to the root cause with regrafting. due to the estimates we had, this uniform estimates on the supremum on the Gromov-Hausdorff distance, supremum over all the times. And I run very late, nobody stopped me. I will take a few minutes maybe towards the end to now give you back the high dimensional torus as an example of our result. This, of course, what is not due
So,
to us.
Anita, let me just interrupt you because there's a question in the chat.
Okay, cool.
And maybe let me just read it out loud, unless the person that asked the question want to ask it now. Okay, I'll read it out loud, then if you want to add something, you can. So, could this also be put in weak Gromov or other topologies outside of Skorokhod?
Okay. Say again, weak?
Weak Gromov or other topologies.
Okay, let's do the following. This is my very last slide. Let me just finish the talk and then we discuss this. Would it be okay?
Right.
Just do this example. No, I want to say that everything was proven by Paris and Revel in this groundbreaking paper. Is that the assumption hold in the high dimensional torus? That means that we I was too fast, sorry. No, I was not. That we not only know that Rn over C is of the order of the square root of the volume, but we know also if we divide by the square root of the volume, we really converge towards a constant square root of alpha d, and that if we divide the square root of this intersection probability by the mean length of a loop erased walk, it's not only of the order of 1 over the square root of the volume, but if you multiply with square root of the volume, it really goes to a constant, and which we can identify. And before I recall to you, identify this constant, let me say that this way to write it allows me to bring the constants on the other side, no? Rather than having just sequences on the left-hand side. And as for the constants, that was also proven by Paris and Revel, is that, 1 second, yeah, here you have it here. You have beta is gamma over square root of alpha d, no? This beta, which we have in front, which is the scaling factor for the edge length, is actually a fraction of gamma and square root of alpha d. And gamma is comes from the mean length of a loop erasure, and it turns out that in the transient regime or high dimensional torus, it's actually you have positive probability for any index to be retained from loop erasure. No, if I do the loop erasure, I will really keep a fraction of all the vertices, and the fraction will be my gamma of d, and it's actually a number between 0 and 1. No, and the alpha of d, it's more complicated. And if I summarize, let's talk about the gamma of d. This is the fraction that I'm retained. I can compare the torus with the lattice, the whole lattice, and then I will see that gamma of d is nothing else than if I would run on the whole lattice 2 random walks and would ask whether one of them never hits the loop erasure of the other one. This is my gamma of d. This is the probability to be retained. And it's very similar to effects you have in finite system schemes, like for the Rota model for densities on the high dimensional torus, where you get also the White-Fisher diffusion in the limit, but with a constant time change. And this comes from the escape probability, not the probability to go to infinity. And the alpha of d, it's very similar, but it's a bit more complicated because it involves 3 random walks. Also intersection events, and I won't be able to explain this in very simple words in 1 or 2 minutes. So therefore, I just give it as information that here you have everything. But the reason it's clearly that the torus is embedded in the lattice, no? That you can identify everything there. And let me say 2 more things. Assumption fail in the 4-dimensional torus, but there's no doubt that, or there is a conjecture that the statement will hold anyway. No, anyway, you have to rescale with Rn over Cn, and you have to rescale edge lengths with Cn over gamma n. That's the nice thing of identifying it, and this one is confirmed by a result by Jason Sweinsberg, in which he proved also a dynamic result, which I skipped for today's talk, namely that if you take loop erased random walk in dimension 4 or on the 4-dimensional torus, then it will show one aspect of my root cause with regrafting process. It will just grow deterministic with speed 1 and then will fall down to random height. No, that's the one which has the Rayleigh distribution as invariant distribution. And he uses exactly these scales, no? Which we have. Or with other words, I can calculate the limits and see that his scales fit with ours. So therefore the conjecture. And now I'm getting a bit more vague. I think assumptions and result clearly fail in low dimension. No, 1, 2, 3. As Roger was asking the question before, but I still have a conjecture. And my conjecture is that if I use the same scales I propose, it will be tight. It will just not be the root cause with regrafting process, because it will just not be deterministic between the regraft events, and also where the cut point falls will not be just uniform on the branch which you already have, but will take the geometry into account. No? And it will be the harder, no? If you come from 1, 2, 3, 1 will be okayish. 2, we have the conformal geometry argument. 3 will be very difficult to do. And that's what I wanted to say. And I think it's a good point to stop to take questions and also to ask answer the question from before.
Thank you very much. Thank you very much, Anita, for this very nice talk. So maybe I let you answer first the question that we had before. You can also just have a look at that in the chat again.
Okay, I will.
If you can, otherwise I can just read it out loud as once.
Maybe I'll do it myself and I stop.
Yeah.
Yeah, I can always open if it's necessary.
Yeah, exactly. Maybe then you can share again. Yeah.
Could this be put in weak Gromov or other topologies? No, I mean, first of all, I'm making a statement about Skorohod topology. There is a little bit of confusion. It will be always the Skorohod topology, but I guess the question is meant to be: could it be a statement about not Gromov-Hausdorff, but Gromov weak or Gromov-Hausdorff weak? No, and for
Yes,
that, yes, no. And the problem we have in the moment, but I see Rouhet is also there. The problem in the moment is that the limiting process, the root cause with regrafting, is not defined with a measure. No, because if I have a measure, then I also need to shuffle around the measure. And this is not there. And this has to be constructed first, and that it's all then easy. And I'm working on this with Rouhet. So once we have this, of course, we would like to show it also in measured topologies. But so far, not even the limit object is there.
Thanks.
I see. Thank you. Are there other questions? I do have one, so let me start. It might
You
be
want me to open again or to?
Oh, whatever. I mean, probably it's just I'm not even sure that it's meaningful, but let's see. So can you imagine also fluctuations around this limit or I don't know, large deviations and the scale of these fluctuations? Do you have any idea of what it can be? Because you're converging to some to process, which is like piecewise deterministic, right?
Mm-hmm.
And the jumps, so the jump time, but then you can just imagine how you fluctuate around this limiting process, right?
No, I do understand your question, but I have not thought about it. I think you have this concentration, of course, for the loop erased random walk towards the one which grows at speed 1. I mean, these kind of statements you can, I guess, derive from these concentration inequalities, but I have not thought about this direction to go.
Yeah, I mean, it seems already quite hard to get the limit already. So maybe, going deeper into fluctuations, maybe also the measuring the distance with the skeleton.
Yeah, but on the other hand, we have all these for deterministic paths, so all these estimates are there. So maybe they give more than I just formulated here, no?
Yeah,
I have to, but
yeah.
I needed to look at it.
Yeah, I see. Thank you very much. Are there other questions? So I think it's also a bit late, so probably we we already had quite a long session. But yeah, so let me thank both of you again, and for this very nice pair of talks that were very well connected, and it was very nice to have the introduction first on the limiting object somehow, and then some dynamic on that, which makes everything harder and more interesting. And thank you very much to both of you.
Yes, thank you.
Thanks again for the invitation.
No,
Yeah.
it was very, very nice. I mean, I think on the dynamic, the dynamic of it's already quite a difficult object to imagine for me. And it was very nice that Ellie gave us this introduction and the limit, but yeah. I see that I didn't really get the problem with the definition of the object of the dynamic in the different space with the measure as well. So you said that the problem is that when you do this jump,
Mm-hmm.
and you have to define what happens to the measure, right?
Yeah, I mean, so far we have this Poisson point process, which is driving a process, no? And it tells me what's happening. But if you have a measure on them, then maybe you can take just a Lebesgue measure if you want. But the point is also that what I presented here was only a tree which has finite lengths. But you can define also the root cause with regrafting if it starts with the CRT. I skipped this part, no? And then you really have to reshuffle measures also, and you cannot do this just based on the Poisson point process.
I see.
And so far, I don't know what the limit, how I would describe the limit process, and maybe I'm thinking too complicated, but I have no.
No, but yeah, I see. Yeah, and do you also have some other dynamics on spanning trees that converge to this limiting dynamic that you had?
I don't know, but I mean, there is another one which is the actually Aldous Broder, because they took a time reverse the random walk, so they are not erasing the edge from the last time you were there to the next step you went, but they wait for the first time you see a vertex, and then they erase the X where you came from. And I'm not sure it's giving you the same or not.
Okay,
I have not thought about it. Maybe it gives you something else.
I see.
But these are the only dynamics I would know in the moment. And
yeah, and it's always somehow a matter of these long loops, right?
yeah. And I think, I mean, you might come up always with dynamics which are changing the trees, but the idea is that it should be a meaningful one. And for me, the meaningful one is that it's actually the one which is behind the proof of the Markov chain tree theorem, which gives a nice formula and has actually a tree dynamic argument in the proof.
No. Okay, no, thank you very much.
Yeah, thank you.
It was very nice. I think what we will do soon is that well, actually, let me just stop the